Hello to all the Form 1 students of St. Martin's. Today, we're jumping right into Mr. George Osafo's workbook to tackle binomial expansion. You know, when you see something like a plus b to the 7th and you just dread the thought of multiplying it out, well, we're going to unlock a really powerful shortcut, a method that turns that long, messy job into something, well, kind of beautiful. Let's get into it.
So let's be real. Expanding this would mean writing out x plus y 7 times and then multiplying everything. I mean, not only would that take ages, but imagine how easy it would be to make just one tiny mistake and mess the whole thing up. There has to be a better way, right? A smarter, faster way to do this, and lucky for us, there is.
Okay, but before we can use this smarter way, we have to make sure our tools are sharp. So let's do a super quick recap of 2 key ideas in math that are basically the foundation for everything we're about to do. First up, the factorial. Anytime you see a number with an exclamation mark after it, it's just a shorthand. So 4 exclamation mark doesn't mean you have to shout the number 4. No, it just means you multiply all the whole numbers from 4 all the way down to 1. It's a really neat trick to simplify these long multiplication problems.
And next, we've got the combination. This formula here, which we say as n choose k, it just tells us how many ways we can pick a small group of things from a bigger group when the order doesn't matter. Now, this might seem a bit random, but trust me, this exact formula is the secret key to solving our big expansion problem. So keep this one in the front of your mind.
All right, with those tools ready to go, let's check out our first method. It's this beautiful visual pattern called Pascal's triangle. Honestly, it's one of the most intuitive ways to find the numbers we need, the coefficients, for our expansion.
And building this thing is surprisingly easy. We just start at the very top with the single number 1. We can call this row 0. Simple as that.
For the next row, we just put 2 more 1s right underneath it. And that's our first rule. You see, the outside edges of this triangle are always going to be the number 1.
And here's where the magic starts. To get any number on the inside of the triangle, you just add the 2 numbers that are right above it. So look here, 1 plus 1 gives us that 2, right in the middle of the next row. And the pattern just keeps going. For the next row, we put our 1s on the outside. Then 1 plus 2 is 3. And 2 plus 1 is another 3. And look at that row. 1, 3, 3, 1. These are the exact numbers you'd get if you manually expanded a plus b cubed. Pretty cool, huh? But here's the catch. What if we need to expand something to the power of, say, 20 or 50? Can you imagine building this triangle all the way down that far? It would be just as slow as multiplying it all out by hand. We need something more powerful for the really big numbers. And that brings us to the master key itself, the binomial theorem. This is the big one. This is the formula that works for any positive whole number power, no matter how big it is. No triangle necessary.
Okay, here it is. Now, I know at first glance this formula can look a little scary. But look closer. What's right there in the middle? It's our old friend, the combinations formula. You see, this theorem is just a powerful recipe that lets us calculate any term in the expansion directly. We don't have to build anything, we just need to know which term we're looking for.
So theory is one thing, but seeing it in action is way better. Let's grab an example and use this theorem step by step.
All right, we're going to expand 2x minus 3 cubed. So, in our formula, a is our 2x, and n is the power, which is 3. Now, what's b? Be careful. It's not just 3, it's negative 3. That little negative sign is so important. We have to bring it along for the ride. Don't forget it.
We're going to calculate this term by term, starting our counter k at 0. So for the first term, we get 3 choose 0, which is 1. Then 2x cubed gives us 8x cubed, and anything to the power of 0 is just 1. Multiply them all together. 8x cubed. Easy. Now for the second term, where k equals 1. 3 choose 1 is 3. 2x squared is 4x squared, and negative 3 to the first is negative 3. Multiply those together, and we get negative 36x squared. See? We just repeat the process for k equals 2 and k equals 3. And notice the pattern. The power of 2x is going down each time, while the power of negative 3 is going up. And now, for the final step, we just assemble all the pieces we made. We line up the 4 terms we calculated, and there it is, our final answer. The complete expansion of 2x minus 3 cubed. No messy multiplication, just a clean, powerful formula doing its job.
So, you've seen the methods. Now it's your turn.
Let's do a quick knowledge check with a few true or false questions, just to see if everything is clicking. Ready? First one for you. In the expansion of 2x plus 1 to the fourth, is the number in front of the x squared term 24? Just think about which term in the formula would give you an x squared. What do you think? True or false?
The answer is true. Absolutely. For the x squared term, k has to be 2. So if you use the formula, you get 6 times 4x squared, which is 24x squared. Fantastic work if you got that one right.
Okay, next one is a little bit of a history check. True or false? Pascal's triangle is named after Sir Isaac Newton.
That one is false. It's named after the French mathematician Blaise Pascal. Sir Isaac Newton's amazing contribution was actually generalizing the theorem so it could work for powers that aren't positive whole numbers. You know, things like fractions or even negative numbers.
Okay, last one for you. If you expand 1 minus x to any power n, will all the terms in the final answer be negative? Think carefully about how that negative sign is going to behave when you raise it to different powers.
And that is also false, because that negative x term is being raised to different powers, 1, 2, 3, 4, and so on. The signs are going to flip-flop. You'll get this nice alternating pattern of positive, then negative, then positive, then negative.
So there you have it. You now have the tools to expand any binomial that has a positive whole number power. But that leaves us with a really interesting question, doesn't it? What happens if the power isn't a whole number? What if it's a fraction? What if you wanted to expand something like the square root of 1 plus x? Well, turns out there's a way to do that too, but that's a story for another time.